Download this code from codegive.com, link in the description below. Debugging Distroless containers with Docker Debug, a comprehensive guide. Distroless containers offer numerous benefits, including reduced image size, improved security, and simplified deployment. However, they can also present debugging challenges due to the absence of a shell and other common debugging tools. Fortunately, Docker provides a powerful debugging feature that can be used to overcome these hurdles. This tutorial will guide you through the process of debugging Distroless containers using Docker Debug, with practical examples and in-depth explanations. 1. Understanding Distroless containers ***. Before diving into debugging, let's briefly understand what Distroless containers are and why they're beneficial. Definition Distroless containers are minimal container images that contain only your application and its runtime dependencies, excluding the operating system distribution layers like package managers, apt, yum, shells, bash, sh, and other utilities. Benefits Smaller image size removing unnecessary components significantly reduces the image size, leading to faster downloads, less storage consumption, and quicker deployments. Improved security A reduced attack surface is achieved by eliminating unused tools and utilities that could potentially be exploited. Simplified deployment Less clutter in the container image simplifies the deployment process and reduces the potential for conflicts. 2. Challenges of debugging Distroless containers ***. The very nature of Distroless images makes debugging tricky. No shell The absence of a shell makes it difficult to directly execute commands inside the container to inspect its state. Docker execute container _id bash simply won't work. Missing debugging tools Common debugging tools like ping, netstat, dump, and strace are often absent, hindering network troubleshooting and process analysis. Limited information Error messages and logs may be less verbose or informative compared to traditional containers with a full OS. 3. Docker Debug, the solution Docker Debug offers a structured and effective approach to debug these minimal containers. Functionality Docker Debug injects a debugging image into your running container, providing a shell and debugging tools without modifying your original Distroless image. This separation is crucial for maintaining the benefits of Distroless. 4. Setting up for debugging Docker CLI ensure you have the Docker CLI installed and configured correctly. Version 20.10 or later is recommended for the best experience. Docker daemon The Docker daemon must be running and accessible. Container to debug You need a running Distroless container to debug. 5. Step-by-step guide to debugging with Docker Debug ***. Here's a detailed step-by-step guide, including code examples. Step 1. Create a sample Distroless application. Let's create a simple Python web server using a Distroless base image. This will simulate a scenario where we might need to debug a real-world application. This simple Flask application exposes a web endpoint at the root path /. Step 2. Create a Docker file. Now, create a Docker file to build the Distroless image. Stage 1, Builder. This stage uses a standard Python image to install dependencies and copy the application code. Stage 2, gcr.io/distributoless/python 3. The stage uses the Distroless Python base image. It copies the built application from the builder stage. It's important to note that this image does not include a shell or many utilities. Create a requirements.txt file. Step 3, Build and run the container. Build the Docker image. Run the container. Verify that the application is running by accessing http://localhost 8080 in your browser. Step 4. Attempt a traditional debug approach, and fail. Try to access the container's shell using docker exec. You will likely receive an error message similar to, error, no such container path, my Distroless app, bash or OC runtime exec failed, container_linux.go 367, starting container process caused, exec, bash, executable file not found in $path, unknown. This confirms that the Distroless image doesn't contain a shell. Step 5, Debugging with Docker debug. Now, let's use Docker debug to access the container. This command will do the following. 1. Identify the container. Docker debug identifies the target container, my Distroless app. 2. Create a debugging container. It creates a new container based on a suitable debugging image. By default, it uses a container with BusyBox inside. This image is specifically designed to provide debugging tools. 3. Mount the target container's file system. It mounts the file system of the original container into the debugging container. This allows you to access the files and directories of the target container. 4. Enter the debugging container. It attaches your terminal to the debugging container's shell. You should now be inside the debugging container's shell, which likely presents a prompt like /. Step 6. Debugging inside the container. Inside the debugging container, you can now use various debugging tools. Listing files. You can list the files in the target container's file system using ls/host. The /host directory typically represents the root file system of the original container. Inspecting processes. You can inspect the running processes using PS, often a BusyBox version. PS auxiliary provides more detail if available in the debugging image. You'll need to look for the Python process running your Flask application. Networking tools, if available in the debugging image. Depending on the debugging image chosen, you may have access to tools like netstat, ping, or telnet to troubleshoot network connectivity issues. For example, netstat. Reading logs. You can examine the application's log files, if any, by navigating to the appropriate directory and using cat or less. Example scenario, debugging a network error. Let's say your application is failing to connect to an external database. 1. Enter the debugging container. Use docker debug my Distroless app. 2. Try pinging the database * inside the debugging container. Attempt to ping the database server's address, ping database_server_address. If ping fails, it indicates a network connectivity problem. 3. Inspect network configuration. Use IP address or similar commands to inspect the container's network interfaces and routing tables. Check if the container is configured with the correct DNS servers. 4. Check application logs. Examine the application's logs for error messages related to the database connection. Step 7. Exiting the debugging container. To exit the debugging container, simply type exit and press enter. This will detach you from the debugging container and return you to your host's terminal. The debugging container will usually be stopped and removed automatically. 6. Advanced debugging techniques. Using a custom debugging image. Docker debug allows you to specify a custom debugging image. This is useful if you need specific tools that are not included in the default debugging image, usually BusyBox. To create a custom debugging image, create a Docker file like this. Build this image. Then, use it with Docker debug. This custom image now includes NetTools, dump, Strace, iproud2, curl, and vim. Asterisk using ncenter, manual approach, less common now. Before Docker debug became widely available, a common technique involved using ncenter to enter the container's network and PID namespaces. This required more manual steps and understanding of Linux namespaces. While still possible, Docker debug is generally the preferred and simpler method. Asterisk port forwarding and debugging over SSH, more complex. For very complex debugging scenarios, you could potentially set up an SSH server within a separate debugging container and forward ports to access debugging tools like debuggers, example for Java applications. However, this is significantly more complex and requires careful configuration. Asterisk logging and monitoring. Asterisk even before resorting to interactive debugging, ensure you have robust logging and monitoring in place. Use structured logging, example JSON format, and tools like Prometheus and Grafana to monitor your application's performance and identify potential issues early on. Good logging can often eliminate the need for interactive debugging. 7. Best practices for debugging Distroless containers. Log everything. Implement comprehensive logging to capture application behavior and potential errors. Use structured logging for easier analysis. Monitor health checks. Implement proper health checks that expose metrics about your application's health and availability. Use tools like Prometheus to monitor these metrics. Consider adding some debugging tools to your Distroless base image, with caution. While the goal is to minimize the image size, adding a few essential debugging tools, like ping or netstat, might be worthwhile if they significantly simplify debugging and the added size is acceptable. Carefully weigh the benefits against the security implications. Use Docker Compose for multi-container applications. If your application consists of multiple containers, use Docker Compose to manage them. Docker Compose simplifies the process of starting, stopping, and debugging multiple containers simultaneously. Automate your debugging workflow. Consider creating scripts or tools to automate common debugging tasks, such as entering the debugging container, running specific commands, and analyzing logs. 8. Conclusion. Debugging Distroless containers can be challenging, but Docker Debug provides a powerful and convenient way to overcome these challenges. By following the steps outlined in this tutorial and adopting best practices, you can effectively debug your Distroless applications and ensure their reliability and performance. Remember to prioritize logging, monitoring, and carefully consider the trade-offs when adding debugging tools to your base images. Good luck debugging. Debugging Distroless containers with Docker Debug, a comprehensive guide. Distroless containers offer significant advantages: smaller size, reduced attack surface, and faster deployment. However, their minimal nature also makes debugging challenging. Traditionally, tools like Bash or Strace are missing, requiring alternative approaches. Docker Debug, a relatively new feature, simplifies this process by allowing you to attach debugging tools to running containers without modifying the original image. This tutorial provides a detailed guide on debugging Distroless containers using Docker Debug, covering 1. Understanding the challenges of debugging Distroless containers. 2. Introducing Docker Debug, key features and benefits. 3. Prerequisites, setting up your environment. 4. Hands-on example, debugging a simple Go application in a Distroless container. 5. Debugging techniques, using Shell, Strace, GDB, and Delve. 6. Customization, debug profiles and Dockerfile integration. 7. Advanced scenarios, debugging multiple containers, remote debugging. 8 Security considerations. 9 Troubleshooting common issues. 10 Best practices for debugging Distroless containers. 1. Understanding the challenges of debugging Distroless containers. Distroless images, as the name suggests, contain only the application and its runtime dependencies. They lack common utilities like *shell *bash, sh, *package managers *apt, yum, apk, *debugging tools *strace, gdb, dump, netstat, *editors *vim, nano. This stripped-down environment makes traditional debugging methods impossible. You can't simply docker execute container_id bash and start troubleshooting. The lack of these tools forces you to rethink your debugging workflow. 2. Introducing Docker Debug, key features and benefits. Docker Debug addresses the debugging limitations of Distroless containers by allowing you to attach debugging tools to a running container. It works by creating a temporary debug container * Docker Debug spins up a temporary container alongside your target container. This temporary container contains the necessary debugging tools. Sharing namespaces * The debug container shares namespaces, network, PID, IPC, mount, with the target container, allowing you to inspect and interact with the target container's processes and network. Automated tool installation * Docker Debug can automatically install debugging tools inside the debug container based on a predefined profile or your specific requirements. Key benefits *. Non-invasive * You don't need to modify your original Distroless image to add debugging tools. This preserves the integrity and security benefits of Distroless. On-demand debugging * Debugging tools are only present when actively debugging, minimizing the attack surface during normal operations. Faster iteration * You can quickly experiment with different debugging tools and techniques without rebuilding the container image. Improved developer experience * Simplified debugging workflow enhances developer productivity. 3. Prerequisites, setting up your environment. Before you start, ensure you have the following. Docker Engine * version 20.10 or later is highly recommended. Docker CLI * corresponding version to the Docker Engine. Go, optional for the example Go application. If you prefer, you can use any language you're familiar with. Kubectl, optional if you plan to debug containers running in Kubernetes. Though Docker Debug isn't Kubernetes specific, it can be used in that context. Verifying your Docker version *. 4. Hands-on example, debugging a simple Go application in a Distroless container. Let's create a simple Go application and package it into a Distroless container. Create the Go application, main.go. This simple application creates an HTTP server that listens on port 8080 and returns a greeting message, including the host name and current time. Create a go.mod file *. C. Build the Go application *. D. Create a Docker file for a Distroless image *. This Docker file uses a multi-stage build. Stage 1. Builder uses the Golang 1.21 Alpine image to build the Go application. Stage 2, Distroless uses the gcr.io/distroless/base latest image as the base. It copies only the compiled binary, myapp, into the Distroless image. Build the Docker image *. F. Run the Distroless container *. G. Verify the application is running *. Open your browser and go to http://localhost 8080. you should see the greeting message. Alternatively, use curl. 5. Debugging techniques, using shell, strace, GDB, and delve. Now that we have a running Distroless container, let's explore different debugging techniques using Docker debug. A. Attaching a shell, bash. This is the most basic debugging approach. Docker debug can automatically install bash inside the debug container. Docker debug myapp starts the Docker debug session for the container named myapp. *image busybox specifies that the debug container should be created from the busybox image. Busybox is a minimal image with basic utilities. You can also specify a more feature-rich image like Ubuntu latest or Debian latest. *bash executes the bash command inside the debug container after it's created. Once inside the shell, you are effectively inside the myapp container's namespaces. You can use tools available in busybox, or your chosen debug image, to inspect the environment. For example, *ps auxiliary, list processes running in the target container. You should see myapp running. *netstatin, display network connections. *lsl/ list the root directory of the target container. *cat/proc/pid/command see the command line arguments used to start a process. Replace PID with the process ID of myapp. Important *busybox is very limited. For more advanced debugging, you'll need a more comprehensive image. B. Using strace to trace system calls ***. Strace allows you to trace system calls made by a process. This is invaluable for understanding how an application interacts with the operating system. Option 1, using a debug image with strace pre-installed, example Ubuntu latest. *image Ubuntu latest, use the Ubuntu latest image as the debug container, which comes with strace pre-installed. Adapt if you have another image with strace. *strace p1f, executes strace inside the debug container, attaching it to process ID 1, myapp. F follows child processes created by myapp. You might need to identify the correct PID if myapp doesn't run as PID1. Option 2, installing strace on a minimal debug image. If you want to start with a smaller image and install strace on demand, you can use the following approach. This requires the debug container to have a package manager, like apt for Ubuntu/Debian or APK for Alpine. Since busybox does not have a package manager, we will use Ubuntu latest. *-c executes a command sequence within the debug container's shell. *apt get update and apt get install strace updates the package list and installs strace. Y automatically answers yes to any prompts. *strace p1f runs strace as before. The output of strace will show all the system calls made by your application. This can be overwhelming, but filtering the output using grep or other tools can help you pinpoint specific issues. For example, you could look for errors related to file access, network connections, or memory allocation. C. Debugging with GDB, GNU Debugger. GDB allows you to inspect the state of a running process, set breakpoints, step through code, and examine variables. However, debugging Go applications with GDB can be tricky due to Go's runtime and garbage collector. Delve, see below, is usually a better choice for Go. First, you need to ensure that your application is compiled with debugging information. Rebuild the application using *flags equals all equals NL, disables optimizations and inlining, which makes debugging with GDB much easier. Then, rebuild the Docker image. Now, run the container with the debug image. Use Docker debug to attach GDB. Inside GDB, you can use commands like *continue, continue execution. *break function _name, set a breakpoint at the beginning of a function. *next, step to the next line of code. *print variable _name, print the value of a variable. *backtrace, show the call stack. Debugging with Delve, Go debugger. Delve is a debugger specifically designed for Go. It provides a more natural debugging experience than GDB for Go applications. First, install Delve inside the debug container. This requires a bit more setup because Delve needs to be able to build the debug container's version of the program. This means you need Go inside the debug container and a way to access the source code. We'll use Ubuntu latest as the debugging image, but this can be made more robust with more configuration. Important considerations ** source code availability * Delve needs access to the source code to function properly. In the example above, it clones a Git repository, but there are other ways to make your source code available in the debug container: volume mounts, copying. * building in the debug container * to accurately debug with Delve, the source code needs to be built in the debug container. Since you may use Distroless, this may seem contradictory. However, the debug image Ubuntu latest still has a lot of useful debugging options that can be leveraged. * port forwarding * for remote debugging with Delve. If you're running the debugger on your local machine, you'll need to forward the Delve port, usually 2345, from the container to your host. 6. Customization, debug profiles and Docker file integration. Docker debug allows you to define debug profiles that specify the image and tools to use for debugging. These profiles can be stored in a dockerdebug.yml file. Example: dockerdebug.yml*. To use a debug profile. Or integrating Docker debug with Dockerfile *. You can add comments or instructions to your Docker file to guide the debugging process. For example, these comments provide a quick reference for developers on how to debug the container using Docker debug profiles. 7. Advanced scenarios, debugging multiple containers, remote debugging. Debugging multiple containers If your application involves multiple containers, you can use Docker Compose to orchestrate them and then debug each container individually using Docker debug. Remote debugging for scenarios where the Docker host is remote, example in a cloud environment, you can forward the debug container's ports to your local machine using SSH tunneling. This allows you to attach a debugger running on your local machine to the remote container. This is most common when using Delve. 8. Security considerations. Privileged access Docker debug often requires privileged access to the target container's namespaces. Be cautious when using Docker debug in production environments, as it can potentially expose sensitive information or allow unauthorized access. Debug image security The debug image should be carefully chosen and regularly updated to prevent vulnerabilities. Use official images from trusted sources whenever possible. Cleanup Always remove the debug container after you're finished debugging to minimize the attack surface. Docker debug should handle this automatically, but it's good practice to verify. 9. Troubleshooting common issues. Permission denied If you encounter permission denied errors, ensure that the debug image has the necessary capabilities, example sys_trace for strace and GDB. Asterisk process not found. Asterisk verify that the process ID you're trying to attach to is correct. Use PS auxiliary inside the debug container to list running processes. Asterisk network connectivity issues. Asterisk if you can't access the target container's services from the debug container, ensure that the network namespaces are properly shared and that there are no firewall rules blocking traffic. Asterisk delve, can't find entry point or similar errors, ensure source code availability in the debug container and that the target executable is built within it. 10. Best practices for debugging Distroless containers. Asterisk use a debug profile. Asterisk define debug profiles for common debugging scenarios to streamline the process. Asterisk keep debug images small. Asterisk use minimal debug images to reduce the attack surface. Asterisk regularly update debug images. Asterisk ensure that your debug images are up to date with the latest security patches. Asterisk use non-root user. Asterisk run debugging tools as a non-root user within the debug container whenever possible. Asterisk monitor debug sessions. Asterisk keep an eye on debug sessions to detect any suspicious activity. Asterisk remove debug containers after use. Asterisk always remove the debug container after you're finished debugging. Asterisk consider logging aggregation. Asterisk for longer term observation, consider a centralized logging solution, rather than interactive debugging. Conclusion. Asterisk. Debugging Distroless containers can be challenging, but Docker Debug provides a powerful and flexible solution. By leveraging debug profiles, understanding the available tools, like Strace, GDB, and Delve, and following best practices, you can effectively troubleshoot issues in your Distroless deployments without compromising their security and efficiency. This comprehensive tutorial covers the key concepts and techniques needed to effectively debug Distroless containers. Remember to tailor your approach to the specific needs of your application and environment.